Hello, and welcome to the next module on finite state machines. As I'm sure you're aware, the finite state machine is a key element in the control strategy for many designs, if not most or all designs. And in this particular section, we'll look at the different types of finite state machines, and more specifically, how to capture them in Verilog RTL. So this is going to be broken into three submodules. We'll review the types of finite state machines before going on to the coding template for the Moore and Mill variants. Then finally we talk about controllers in general and the role of reset. And the references are given at the bottom there. So you must recall there are two basic types of finite state machines: the Moore machines and the Mealing machines. In a Moore machine, the outputs depend solely on the state vector. And you can see that here in the logic. Here we have the output logic producing the control signals. It depends solely on the state vector. Of course, the next state logic depends both on the inputs and the current state vector. In contrast, in Mealing machines, the outputs depend on both the inputs and the state vector. So here you see, for example, you have this additional set of lines here coming from the inputs to the finite state machine to the output logic that is producing the control signals. In general, it is best to go with Moore machines in synthesizable designs, and the reasoning is quite simple. It is a good practice to put finite state machines in a module by themselves, and in doing so, you also need to make sure that there's a flip-flop between any primary input to that module and any output of that module, so as to prevent unconstrained paths. You might recall we talked about this in the Verilog 2 notes. In Moore machines, there are no unconstrained paths. All possible logic paths from the input to the outputs has to go through the state register. In contrast, in a Mealing machine, there are paths from the input to output that do not go through the state register. If the finite state machine is in a module by itself, this can lead to unconstrained logic paths. There are two ways to fix that. One way is to constrain the paths by hand, which is very tedious. The other way is to put the finite state machine into a module as part of a larger design that does have registers between the inputs and outputs of that module. We'll talk about this again when we get to the hierarchy notes. The finite state diagrams associated with each machine and the timing associated with each machine are quite different as well. In a finite state diagram for a Moore machine, we label each state with the outputs settings associated with that state, because the output depends solely on the state. We label the branches with the input that determines the branches. So for example, on the left here we have a simple finite state diagram. We start in state 0, where the output is 0, 0, 0. On the next clock cycle, because I don't show a feedback structure here, on the next clock cycle, if the input is 0, we go to state 1. If the output is 1, we go to state 2. While we're in state 1, the output is 0, 0, 1. While we're in state 2, the output is 0, 1, 0. So this is the general structure for a Moore machine. Let's look at the timing of this particular structure. Here I've shown the clock and the variable in. I'm assuming this we start in state 0, and I'm presuming we're transitioning to state 0 on the rising edge of the clock. During that clock period, the input is 1. But before we do that, let's look at the outputs. Of course, while we're in state 0, the output is 0, 0, 0, as specified by the logic structure on the previous page and the finite state diagram here. Because the input is 1, that tells us on the next state, in the next clock cycle, we're going to go to state 2. So we go to state 2, the state register changes to state 2 on the rising edge of the clock. The output is now 0, 1, 0 after that rising edge. Notice that the output in response to the input took a 1 clock cycle delay. This is expected when you see that when you go back to the logic structure, any change to the input will take 1 clock cycle to influence the output here because it's going through the state register. In contrast, in a milling machine, we associate both the inputs and the outputs with the state transitions. So this is a fairly similar finite state diagram in a Mealy format. We have state 0. If while we're in state 0, we have input 0, the output immediately changes to 0, 0, 1 after only combinational logic delay, and we go to state 1. In contrast, if the input is 1, the output changes immediately to 0, 1, 0, and we go to state 2. Again, here's a timing diagram down below. Assume somehow we transitioned to state 0 on this rising edge clock, and in became 1 during that clock period. This means in the next clock period we're going to go to state 2, but notice how the output is quite different than the Moore machine. Because the output is associated with the change of input, the output changed to 0, 1, 0 during the clock period in which the input changed to 1. Thus, the output changed 1 clock cycle earlier than in the Moore machine. This might be why you might want to use a Mealy machine in some designs, because this property of outputs responding to inputs more quickly. We also have to discuss the different ways to encode the state vector. There are 4 commonly accepted alternatives. Minimal encoding, that is minimum number of bits. That is, of course, n bits in the state vector can encode up to 2 to the n states. Often we express these sequentially. However, that does not necessarily lead to the minimum logic in the combinational logic blocks here. You might recall from your undergraduate days or your earlier days as an undergraduate that there are ways in which to do the state sequence optimization so as to minimize that logic. Synopsys can do that for you, but we're not going to cover that as part of this class. So normally, when the natural tendency and the usual approach to encode the state vector is to do minimal sequential encoding. That is, the states are numbered in sequence, in some sort of natural sequence, such as top to bottom, left to right on the previous page. You might also want to do gray encoding. In this, you might recall the state bit will only change by only 1 bit between sequential states. This has some minor advantages in minimizing the transitions in the state vector, and you might recall we did use this explicitly when we're going between different clock domains, but you wouldn't expect that to apply here. One-hot encoding is also a fairly common encoding technique. Here, for 2 to the n states, we have 2 to the n bits in the finite state machine. That is 1 bit per state. The big advantage of one-hot encoding, it leads to a much faster finite state machine, because you don't have to have any decode logic to work out what state you're in. And in fact, a common approach in designing finite state machines is to start with minimal sequential encoding, possibly applying the Synopsys, the synthesis tool's finite state optimization to it to speed it up a little bit. But if that isn't fast enough, that produces a finite state machine that cannot meet the desired clock period, then just switch to one-hot encoding and you get an immediate and quite substantial decrease in the achievable clock period for any particular finite state machine. Let's look at a simple example on the next 3 pages. Let's say we have 7 states in a finite state machine, and we're going to encode the first 3 states using each of the 3 major styles on the previous page. Well, what would you expect to see? Minimal encoding is just binary 0, binary 1, binary 2, sequentially drawn out. Gray encoding, only 1 bit changes per cycle, so you get a different count sequence in the binary representation of the decimal numbers. 1 hot encoding, 1 flip-flop has 1 stored in it for each state, and only 1 flip-flop has 1 stored in it for each state. So state S0, that's flip-flop 0. State S1, that's flip-flop 2. Correction 1. State S2, that's flip-flop 2. And so on. State S7 would be flip-flop 7 containing 1 and everything else being 0. We also have to decide how reset is going to be applied to the finite state machine. Your reset strategy should be common across the entire chip, thus it's really identified by your design methodology manual in your particular design group. All finite state machines should have reset going to them. You recall reset is a golden signal coming in from outside your design. It only occurs on power up, or for some other reason you need to reset the chip into a known state. For example, if you have a hard reset button on your device, or if you have, or somehow you get issued a reset interrupt on a programmable device. At the logic level, there are 2 types of resets: asynchronous and synchronous. We talked about this in the flip-flop notes in Verilog 2. In asynchronous reset, the FSM goes to the reset state whenever reset occurs, and doesn't have to wait for the next clock edge. In a synchronous reset, the FSM only goes to the reset state after the next clock edge. I don't care which you use in this class. The asynchronous reset does have slightly smaller flip-flops, but a synchronous reset is safer because noise on the reset line, at least away from the clock edges, won't lead to a false reset. Another thing you have to consider when coding a finite state machine is fail-safe behavior. That is, can you recover the finite state machine if it somehow gets into an illegal state, for example due to a noise event? Obviously you do want to be able to recover the finite state machine if that happens. Here, because I use minimal encoding for this 4-state state machine, it is actually possible to accidentally end up in state 3, that is encoded as 1-1, because of, say, a noise event. Notice there's no arrow going to state 3. That's how I know it's an illegal state. However, if I'm in state 3, I want to get back to a known state sequence. So here I show it going back to state 0. Sometimes it's also useful to register outputs. For example, what this does is resynchronize the outputs of the finite state machine, starts a new clock period, essentially pipelines the control, sometimes permitting the design to operate faster. However, it does of course lead to an additional clock period of delay from the state vector changing to the control impact changing on the data path the finite state machine is controlling. That brings us to the end of this submodule. I remind you, in a Moore machine, the output depends solely on the state vector. In contrast, in a Mealy machine, the output depends both on the state vector and the inputs. The Moore machine is a preferred machine if it meets your timing intent. However, the Mealy machine, because it's easier in synthesis. However, if you need to use a Mealy machine in order to have the outputs react 1 cycle sooner to changes in the inputs, then that is fine. You'll just have to manage synthesis by having a coarser hierarchy. The state encoding does have a big impact on the speed of the state and the state transitions. You'll tend to either use minimally encoded vectors, that is n bits encoding 2 to the n states, or 1 hot encoding in which only one flip-flop is high for each possible state. And of course, reset should be applied to all the finite state machines in your design. There's a short quiz following this, and I suggest you move straight on to the next submodule after that, because there we review the different coding styles. I will see you then. Thank you.